Hi everyone. In this lesson, we will create the Simulink model for the mass spring damper system in the Kalman filter implementation. Okay, and first of all, we need to create some init function for the MCK system to load some data to the Simulink. Okay, and so the clear all, close all, and CLC should be given in here, and so we are one MCK system and M should be given in here. First of all, the constants can be given by the M is equals to the 1, C is equals to the 2, K equals to the 1, and the general constants can be defined with the M, C, and K. Okay, and so the Kalman parameters should also be defined in here. dt is equals to 0.001 is the 1 millisecond, and the measurement noise variance mn std 0.04 and mnv mn std times mn std, and the process noise can be defined with the pn std is equals to 0.002. okay, and also pnv is equals to the pn std times pn std. okay. And also we need to define the qnr parameters in here. qnr, so the q is equals to 0.0001 times I2 times PNV, and the measurement Kalman matrix is defined with the H1 0 and 0 1. okay. And C is the are real measurement parameters. okay, and 0 1. At this case, we measure or obtain the two sensor values in here, position and the velocity values. okay, and so the R is equals to the 001 times I2, this the identity matrix, times M and V. okay. So initial conditions should also be given in here. Init count continuous parameters, which is given by with the 0 and 0, and init count continuous is the same with this one. okay, this is the discrete parameters, and also we need to give the p init disk body mnv times I2. This is the error covariance matrix. okay, and so this matrix should be initialized with the measurement noise variance values. okay. So these are the basic settings, and then we need to create the blank model in here, just like this one. And so we need to push to right click, model configuration parameters should be set with the not the variable step, it's the fixed step, and 1e minus 4. okay, and also we need to give to the model properties, the callbacks init function should be initialized. This is the function at the beginning of the the model is run. okay. If I run this code, and then this init function is called first. okay, and so we'll run MCK system, and apply should be given in here. okay, so first of all we need to save this function. We'll run MCK system. okay, MCK Kalman. So we need to add the Matlab function body in here in order to build our model. okay, and so this is the real physical system. okay, So real physical system. Okay, and first of all we need to give the z and rand number to generate to what? To random noise. From here, f is the input, the general constant should be given in here, and the c, the greater c, should be given in here. This is the output matrix. Okay, and so after that we generate or return to the what? The z dot and y out values. Y out, the r measurements. Okay, and so first of all we need to define the output. Z dot is equals to the what? A times z plus b times f. Okay, and also the r measurements. Y out is equals to what? C times z plus rand number. Okay, in this case we have only the measurement error, not the process noise. Okay, and so if we don't have any process noise, and then we will set to the what? To this q parameter is to what? Is to 0. Okay, this is another example of utilization of the Kalman parameters. So we need to define the matrices in here. The A is equals to the 0 and 1 and K M and C M. Okay, and the B is equals to the what? 0 and 1 divided by M. See that this is the continuous system. Okay, and also the constants can be given by with the M is the general constants 1 and 1 is coming from the M function, and C and K and Q and 3. Okay, these are the real physical system body. Okay, this is real system, and after that we need to give the integrator values at this one, the z dot, and so this is the init count. Okay, and so this is the 2 times 1 vector, and also we need to define the goto from this is the goto, and this goto is assigned with the values of the z, and after that we can put to what? This is the z. Okay, and so we don't need to use the this line in here. Just like this one, we can define the this goto and from, and so this connect the output of these terms into the this one. Okay, this is simple. And also we can define the new parameters in here is the y, this is the output, this is the measurements of the R system. And also we need to define the constant values in here, constant. Okay, and so this constant should be initialized with the what? With the general constants. Okay, and also this is equals to what? The C. Okay, this is the output matrix. And also we can build to what? This is equalized with the what? The force value here. Okay, and also we need to find what? The rand number. Okay, these are the basic system, and so separately we define these values in here. Okay, first of all, so we need to move to the what? To the force generation. So in order to create the force generation, we need to add the Matlab function body, just like this one. And so no, this is the force generator. Okay, and so this force is assigned to this one, and so also we need to give the clock here. Okay, to emulate our system. And so this function t, and after that the output is force, and so the end, and the force is assigned with the what? The force is equals to cos 2 times t. Okay, just like in this our simulation for the mass spring damper system. Okay, this is the force definition, and so this is okay. So how about the generate the random noise, just like this one? And so we can put to what? The random number generator, just like these ones. Okay, and so we can put the two values because we measure the position and the velocity values, and so we always use the mux values to combine these terms into the what? Into transferring to 2 times 1 vector in here. Okay, so how about this one? This one is mean the 0, and Marianne's is assigned with the m and v values, and so this should be equalized with the what? With the dt value, right? And also so we can assign the other parameters, the mean 0 and m and v, and dt should be given in here because it's the r sampling rate. And so if we have the any noises in here, and so the r noises is scaled with the what? With r the sampling period, guys. Okay. So after that this is the basic definition of the what? The r noises and the forces, and so we can assign to what? Noise and force generation. Okay, these are the section, and also we should give the what? The greater see here. Okay, and so how, and then we should assign the physical system just like this one. Physical system. Okay, this is our physical system, and after that we should build to the what? To our nation. But in the first place, so we need to firstly we need to start the code. The scope should be analyzed in here in terms of the position velocity value. If we run this code, and then there should be no error in here, and then if I open this code, and so see that the one of them is the position, the other one is the velocity values. Everything is okay right now. And so how we can define the Kalman parameters or the Kalman function in here? First of all, just like the previous case, we need to build the Matlab function. In the real-time implementation, you should put your code into this one. Okay, the Kalman filter designs. Okay, and so if I put these ones, and so these ones, and after that, first of all, the y should be taken in here. This is the Kalman filter design, and so the y, the measurement should be taken, f should be taken, y filter int value should be taken because it's the previous and the present state should be used in here, and also the p int value is we update the prediction rate or the covariance rate of the error signals in here, and so the general constant should be given in here, and q, h, r, and dt. You can use or you can build this function just like this one, and so we need to put out to the what? The y filter values and the p disk values. Okay. These are the case, and after that this is the case, and so we need to put the whole these connections just like this one. First of all, we need to give the unit delay function. This is the z domain function in here, just like this one, right? Because it's a discrete process, and so this should be initialized with the what? With the init count disk value. But you should remember that this should be assigned with the dt values. Okay, this is our sampling rate, not just the what? Not the Matlab Simulink rate. Matlab Simulink rate is equal to what? 0.1 0.1 milliseconds. Okay, but our Kalman filter is run on the 1 milliseconds. This is important. And after that, we need to give to what? This is the y, this is the measurement. And so we need to put to what? This is the y filter. Okay? So this y filter is put into the what? Into the y filter int. Okay? And also we can put the force values in here. And also this is the y is coming from the system measurements. Okay, this is the measurements. And also we need to give the some constant values in here, just like this one. This is the dt values. We can assign the dt in here, and also we can assign the r. Okay, and also we can assign the h. It's coming from the init cont function, and also we can assign the q values. It's 0, but it's not important for our case. Okay, because if we have the any process noise, and then we will have the different model. And so this is the generalization of the Kalman filter process. And also the general constant is assigned with the general constants. Okay, this is general constants. And also we need to give this one unit delay. And so this is initialized with the p init and disk function body. And so this dt. And also we can assign the goto with the what? With these values, with the p. Okay, and this p is what is put into this one. This is the pk plus 1, and this is the p, because we use the unit delay in here. And so we can generate what the xk or the pk from what pk plus 1. Okay guys, and so how we can build these values? First of all, we need to write the constants values, just like this one. The m is the general constants 1 and 1. Okay, so the c and k should be given in here, and so after that the system matrix should be given in here. First of all, the ATR is equals to what? The discrete state space form 1 dt. Okay, and so 1 k times dt divided by m, and so the 1 minus dt times c divided by m. Okay, this is the state transition matrix for our discrete state space, and BTR values is equals to what? The 0 and the dt divided by m. Okay, these are good. And so how we can calculate the Kalman gain in here? First of all, we need to build the z disk value. This is a discrete, the estimation state. And so the ATR y filter int, right, plus BTR times f. Okay, and so the p disk int value is equals to the what? ATR times p int plus ATR transpose plus q values. Okay, and so the compute Kalman gain. The Kalman gain k is equals to what? The p disk int times h transpose times inverse h times p disk int times h transpose plus r. Okay, and so after that we need to correct the r observation, or the r measurement is to what? Is this one, the y filter. This is the filtered output, Kalman filtered output, z disk values plus k times y. This is the r measurement coming from the system. It's the noisy signals, h times z disk values. And after that we need to update the covariance error matrix. P disk p int value minus k times h times pi p int. Okay, this is the Kalman code, and so it's the important in your CPP or C application. You just only utilize this body. Okay, CPP implementation contains only this code, not the other ones, because the other ones is already given in your real system. Okay, and this is the real-time code to implement your code notation in the Kalman filter implementations. Okay, so this is the Kalman. Kalman filter. Okay, so we need to show the results of these terms in here, just like this one. First of all, we need to use the Y filter in here. Just see that the Y filter should be demuxed. Okay, converting it to the what? Into the two terms. And also, this is Y filter. We should put the mux values to compare the R signal based on what? The noisy one, right? And so the Z signal is also should be taken in here. This Z is a noisy signals, guys. Okay, no, this is not the yes, this is the noise signals, because in the Y out we add the rand number in here. Okay, and so this should be put into the what, and so the first values should be compared in here in the scope. Okay, and so the one of them is the real response, the other one is the what? Is the Kalman response. Okay, so p int value does not found in here, just see that, and so the p int sorry, I said the p int, so the p int, tamam, okay. And so if we rerun this code, and then we will have two response. See, in this two response we have the Kalman gain, just see that is improves the R data in here, but in the random noise generates what the different signal values in here. For example, this is the first state of the R Kalman filter output, and so does not match these signals in between to the each other, but because we have a greater difference in here, because the rand number is too high in here. And so how we can prove that? If we want to prove, just see that this Y should be taken in here, see, and so this Y should be demuxed in here, and so this mux also be taken in here, and so this one and this one should be taken in here, and so this Y is the real measured signals in our system. And so just see that this R signals is returns to the what? To this one, right? And so this is R signal, but the yellow one is the what? Is the Kalman filtered signals in here. Okay, guys? So this is important for our study, and so we can remove this connection in here. Okay, the Z2 body or the velocity is compared with this one right now. Okay, and so if we run this code, then we will have the what? The velocity in comparison in our code. Just see that in our code the yellow one is the Kalman filter response, the other one is the measured signals in here, right? Because the Z generates to what? Some unwanted noises in here, right? And so this blue line is the Y or the measured signal from the sensors, but the Kalman filter generates what? The two good signals in here, and it's filtering the R whole the process. This is a good results. Okay, and so how we can analyze the Y filter and to what the velocity values of these terms, just like this one. And so the Z values, the velocity comparison of the what the noisy and the Z signals in here. This is the measured signal from the sensor measurement, and so this is the ideal signals in here. And so the ideal signal, just see that the ideal signal is different from the what, from the measured one. Okay, and so this measured one returns to the what, to the other results. And so the Z is the ideal response of the RMCK system, but the sensor reads to what, to some different signals in here. Okay guys, and so if we compare the positions value, just like this one, see, I'm sorry, okay, if the position values is different from this one, just see that we have the noise signals, but the other signals is the real ideal signals. Why is this happening right now? Because we assign the Q values. If you know, the process noise does not exist in your system, but still we need to utilize these terms. Just see that. See, this is the last one. And so this Q is assigned to what? To this value, for example. And so if I rerun this code, just see that right now. See, these two signals is closing to each other right now. And also we can set the different values of this one. That's the Q, and R is set, and the Q is smaller and smaller right now. And so if I rerun this code, this position Y filter, the filter signals, and the what, the noisy signals, is closing to each other. For the worst case, just see that. For example, Q, this one, and so this is the what, 0, 0, 0, 0, 0. If the Q and R is taken to the smaller values in here, just see that these signals is closing to each other, but this is not a useful method to what, to test it, because we don't have, if you don't have any process noise in here, just like this one, and so we don't have any process to suppress the Q signals in here. But if I choose to what, to these signals into the what, the 100s right now, and this Q is very, very small, okay? And so if I rerun this code, this Simulink code, just see that. First of all, we can compare the Y filter and the Z response. These two are different from each other, okay? But the one of them is true. The blue line is not true because it's the ideal, but the yellow line is the measured signal from the signals, okay? And so how about the velocity values? Just see that these velocity values is sampled with what? With this nomination, and so that's a good results. But the positions values, Y filter and Y, is compared right now. This is what? This is different. But just see that I'm returning to the what? To this value. The position value is assigned in here, and so see that the R signal generates the different response in here, okay? Because the measurement is different from each other, and the velocity values is what is taken from this system, okay? And so this is the basics of the what, the Simulink Kalman filter design. And so you just need only utilize these terms in here in terms of the what are nomination of the codes, okay? And so you just need to implement this CPP code just like this one, guys, okay? Okay, see you guys.